look in the noise. And for our investigation, we decided to explore a distant space object with a low signal to noise ratio. For our object, we decided to use the M101 Pinwheel Galaxy. It is a spiral galaxy located in the constellation Ursa Major. Its coordinates in declination and right ascension are displayed here. The distance to the galaxy is 6.4 megaparsec. On the diagram of galaxies of Hubble-Devoucouleur, it sits right here on the branch of intermediate spirals. The main components of a galaxy are a bulge, which is the central cluster of stars. It consists of mostly older and more red stars, while the disk is a place with active stellar formation and intensive H2 regions. So our goal will be to achieve a photometric decomposition of the galaxy M101 from the observations in BV and R filters, and to determine the bulge to disk ratio for the luminosities of both components. Our hypothesis is that this will exhibit a very low signal to noise ratio near the edge of the galaxy. For our observations, this is the telescope that we used. It uses a Schmidt-Cassegrain optical system with a 14-inch aperture. The CCD camera we used for observations is listed here, its dimensions and the size of 1 pixel. And we also used filters and BV, R, and I with 45 millimeters of diameter. For our theoretical basis, let's first define illuminous as the quantity measuring the total luminous flux incident on a surface per unit area. However, in astronomy, we use a relative measure known as the apparent magnitude, which is the relative brightness. An increase in 5 magnitudes corresponds to 100 times decrease in brightness, and it is calculated using the Poxton's law. We then define surface brightness as this apparent brightness per unit solid angle of the object. And since the intensity and solid angle drop according to a inverse square law, surface brightness does not depend on the distance to the object. The difference in the change of the surface brightness in the components corresponds to different laws, the disk law and the Devoucouleur law, which are shown here. For the software and data analysis we used IRIS, which is a software for processing images, and data we obtained in Microsoft Excel for data analysis. First thing we did was to fit isophotes onto the galaxy, which is an isophote is a curve connecting the points of equal brightness, and these isophotes are generally defined by the Fourier expansion of the deviations from an ellipse. We used this profile here to define the Fourier coefficients for every isophote and to center it onto the galaxy of the frame. Then we estimated the background intensity and took the mean intensity. The standard deviation from this background intensity will serve as our noise in the background. The values we obtained are displayed in the table below. For our experiment, we fitted isophotes with IRIS and calculated the instrumental surface brightness to the catalog brightness that is generally accepted using the formulas obtained below, where K and D are coefficients that are obtained from a manual that is provided by the website to calibrate the brightness. This is the graph that shows the calibration. As you can see, the intensity near the edge of the galaxy drops rapidly to 9.73 counts per pixel, starting from more than 500. This again exhibits the behavior of a very weak signal near the end. Same is true for the signal to noise ratio, where it is below 2 in the visible filter near the end of the galaxy. For our experiment, We derive the divocolor profiles of the galaxy by graphing the surface brightness as a function of distance from the center, and then we separated the bulge from the disk using the magnitudes from 100 to 300 arcseconds distance from the center and applying the disk law. Then we interpolated the bulge with the divocolor law. The obtained surface brightness in our filter is displayed on this graph as it changes. And all three obtained divocolor profiles are displayed here. As you can see, the most prominent, the galaxy is more prominent in the R filter. Then we use the disk law to obtain the relevant parameters. As you can see, the line crosses all error bars, which gives more accuracy to our measurements. And these are the values we obtained for these relevant parameters in R. These are the relevant parameters for the bulge, again in R, and the same is true for the interpolation using the divocolor law. We then used integral parameters we calculated the integral parameters of the galaxy, such as the absolute magnitude of the bulge and the absolute magnitude of the disk, using the relevant parameters we obtained before, where we used the effective radius, which is the radius that encompasses 1/2 of the brightness. And then we used the brightness at that radius, which is the effective brightness. We calculated these parameters and then obtained the relation for the bulge to disk luminosity ratio using Poisson's law. The result obtained for each of the filters is displayed here in this table. And for our signal to noise ratio calculation, we use the intensity per pixel as our signal and the noise to be the standard deviation of the mean intensity of the background. We then see how the signal to noise ratio drops rapidly from the center to the edge of the disk, where it is near to 2 in its value. Then we fitted the models of these laws onto the profile. Here is the profile in B, and here is the profile in V and in R. This agrees with our theory, since since the surface brightness drops linearly with respect to R, and in the bulge with respect to R to the power 1/4. The signal to noise ratio also drops rapidly near the edge of the galaxy, where it is significantly low. In conclusion, this provides a meaningful way to obtain astronomical observations using very weak signals. And the experiment demonstrates discerning of these very weak signals, especially near the edge of the galactic disk. Thank you for the attention. I am sorry, but we cannot hear you currently.
Okay, sorry, I was muted. And I say thank you, reporter, for your report. And now we move on to clarifying questions from the opponent, please.
Hi, Amyan. So I just want to first of all thank the reporter for that presentation. But I have a few questions. So first of all, what have you defined as a distant space object?
Can you please rephrase the question? I didn't hear you quite well.
That's fine. What have you defined as a distant space object?
Well, in this case, we defined a distant space object as the galaxy M101. Since this galaxy is 6.4 megaparsecs away from the Milky Way, it is in no way calculated, it is no way connected gravitationally to the Milky Way. And this is a sufficiently distant space object. In fact, the Hubble's law for the expansion of the universe starts to be relevant for this object.
Thank you. Just on that, so you were investigating a individual space object or just multiple?
We investigated the galaxy M101 in all three filters, in the blue, visible, and red light filters, respectively.
Great. Um, so for when you calculated the sound to noise ratio, did you use an average for that or?
We use the standard deviation in the mean intensity of the background as
Okay.
our noise, and our signal was the intensity per pixel obtained using the Iris software program.
Great, that was very
And
good.
this is
Thank you.
how we calculated the signal to noise ratio.
How did you define the edge of the bulge?
Well, the edge of the bulge isn't very, there isn't a strict definition to where a bulge ends and where the disk starts. However, this can be obtained by the models we fitted with the laws. The Devaux-Color's law is valid for the bulge, and the disk law is valid for the disk. These different changes in the surface brightness
Okay, could you go
correspond to
back
the
to your
way we
slide?
differentiate.
Could you go back to
Ex-
your slide and show us the laws? I'm not
the
sure what
laws,
number it was. I don't think you had slide numbers.
yes.
Thank you.
Uh, Here are the laws.
Yes.
These are laws that are obtained empirically from observations of many galaxies, and these coefficients are determined
Do you
to be
have
like that
any
because they fit many.
do you have any rule calculation or like how did you use this in your calculations?
Well, the graph obtained for the Devaux-Color's law is linear with respect to the radius to the power 1/4. And when we fit it onto the model, you use the slope and the term in order to determine the effective
Okay,
radius and
okay,
the
we're out
effective
of time.
surface
We're out
brightness.
of time. I'm sorry. We're out of time. Thank you very much, opponent, for your questions, and thank you, reporter, for the answers. We now move on to the preparation time for the opponent, please.